As we know, the difference between an ideal gas and a real gas is that ideal gases do not have any interactions between them. We know this is not true for real gases because gases can be condensed to become liquids, and the whole reason something is a liquid is that there are interactions between particles which keep the particles close to one another and define the liquid state. We know the equation of state of an ideal gas, which is PV equals nRT. So the question that we will answer in this video is, what is the equation of state for a real gas? To understand real gases, we need to understand the internal energy of a gas system. The internal energy of the system is made up of the energy of each particle, the sum over energy of each particle, plus any energy of interactions. For an ideal gas, this energy of interactions is 0. For real gases, we may have attractive interactions, in which case we will lower the energy of the system, so attractive interactions have negative energies, or repulsive interactions, which would raise the energy of the system. So repulsive interactions have positive energies. Typically, we're only worried about attractive interactions because the particles never get close enough to each other to have repulsive interactions. On a macroscopic level, we can investigate the result of these interactions by thinking about what happens to our gas particles when we expand or contract the system. So if we change the pressure or the volume of the system, what's going to happen is the particles are going to move further apart when we expand the system and are going to get closer together when we contract the system. Remember that we model these interactions with a Lennard-Jones potential. And the Lennard-Jones potential looks at the energy as a function of distance between particles. So at very large distances, there's little interaction, and as we move them closer together, they attract one another, and that lowers the energy of the system. As they get too close together, they repel each other, and that raises the energy of the system. For real gases, we're typically looking at distances in here where the attractive interactions are dominant. So if I have a compressed system, then I'm decreasing the distance between particles, and my attractive interactions are greater. And as I expand the system, I have larger distances, and so my attractive interactions are less. On a macroscopic level, we can investigate this by thinking about how the energy changes as I change the volume at constant temperature. This term will be 0 for an ideal gas because all of these systems have the same energy, since there are no energies of interactions, and moving the particles closer or further apart doesn't change the energy of interaction. So that derivative is 0 for an ideal gas. If there are interactions, then this term is not 0 for real gases because this interaction term is not 0, and so when we take the derivative with respect to volume at a constant temperature, we get a non-zero derivative, even though this is constant with temperature, this is not, and therefore we get a non-zero derivative. It turns out that we can relate the pressure of a gas to the derivative of the Helmholtz free energy with respect to volume at constant temperature. The Helmholtz free energy is equal to the internal energy minus the temperature times the entropy. And so this derivative of Helmholtz free energy with respect to volume contains a derivative of the internal energy with respect to volume, and thus tells us about the interactions. Remember that the pressure of a gas is the force per unit area, so it depends on the force with which particles hit the walls of the container. And if there are attractive interactions between particles, then the particles are going to hit the walls of the container with less force, causing the pressure to be less. However, if there are repulsive interactions, then that pressure is going to be greater because the particles will hit the walls of the container with a greater force since they're repelled from the other particles. On a microscopic level, we can model the pressure by using our partition function and looking at the Boltzmann constant times the temperature times the derivative of the natural log of the partition function with respect to volume at constant temperature, constant energy and number of particles. So the partition function for this complicated system includes the energy of each particle plus the energies of the interactions of each particle with all the other particles in the system. So this is a very complicated partition function. But suffice it to say that when we do this, we end up with a series expansion where the pressure is equal to the gas constant times the temperature times a series in 1 over the volume, where the first term is just 1 over the volume, and the second term is quadratic in 1 over the volume and includes a coefficient called the second virial coefficient. We can include higher order terms in the expansion that would be cubic in 1 over the volume, quartic in 1 over the volume, and so forth. This term is called the second virial coefficient, and this equation is called the virial equation of state. When the second virial coefficient is 0, we end up with the ideal gas law, PV equals RT. So B2, a function of T, is equal to 0 implies that we have an ideal gas. However, if the second virial coefficient is less than 0, then we have a real pressure that is less than the ideal pressure. There's the ideal pressure. If this is negative, we subtract something from the ideal pressure and we get something less than the ideal pressure. When the real pressure is less than the ideal, what we expect for an ideal gas, that would indicate that we have attractive interactions between particles because the particles are now hitting the walls of the container with less force because they're attracted to the other particles. Thus, a negative second virial coefficient indicates attractive interactions are dominant. When we have the opposite case, then the real pressure will be greater than the ideal pressure, and that would indicate that repulsive forces are dominant. Another familiar equation of state is the van der Waals equation. When we model the interactions with a Lennard-Jones potential, we can show that A is equal to this and B is equal to this. Notice that the A term contains both the depth of the Lennard-Jones potential, or the strength of the interactions, epsilon, and the Lennard-Jones potential distance cubed. So this R Lennard-Jones is the distance of closest approach for two particles. And so if I cube that distance of closest approach, I have something that's proportional to the volume of a particle. Notice that the B term contains only this term that is proportional to the volume of a particle. Both terms contain Avogadro's number, and so this is per mole of particles. Thus, we typically think about this parameter B in the van der Waals equation as being related to the volume of a particle. So B is proportional to the volume of a mole of particles, the molar volume. Notice that if we take A and divide by B, then the part of each of these expressions that contains the radius cubed, so the part that is proportional to the volume of the particle, will divide out, And we can then see that A divided by B will be proportional to epsilon, which tells us about the strength of interactions between particles. So A is related to the strength of interactions between particles, but really to fully understand the strength of those interactions, we need to look at the A term divided by the B term, which will give us something that is proportional to the strength of those interactions.